Hi kids, we are back for another lesson of AP Calc. This one's on section 6.4, accumulation functions, and actually has something in that is very important to us called the fundamental theorem of calculus. So one of the things you want to take note of is that we're going to skip practice number 20. You do not have to do that. And so in the last lesson we learned about the definite integral, right, going from a to b, a lower limit and upper limit of some function with respect to x, represents the area under the curve of f of x on the interval from a to b. Let's say we know the interval starts at a, but we don't know where it stops. It keeps going. That would give us, if I were looking at it, I'd have an a value that is a, but my b value would be x. We don't know where it stops. It stops at some x value down the line, where a is a constant and x is some unknown variable. We can represent that as a new function that looks like this. Capital F of x, take note of that, capital F of x equals the interval, or the integral from a to x, right, b and a. And then you have to use a variable other than x because x is already used as where your stopping place is. And that stopping place isn't part of your function. So they usually use f of t dt. So one of the things you want to make note of is that it has to be a variable other than x. Okay. So number one says, let capital F of x be the integral from 0 to x of f of t dt. Use the graph of f in the figure to find the values of the table on the interval from 0 to 5. So we're going to go out to the margin, and I'm going to show you in detail how this whole thing works. So if I want to know what it is when x is 0, think about how the integral would look for that. Your bottom is 0. Right, I'm looking at this. Bottom is 0. Your top is the x value they give you. And then you've got the function f of t dt. Now I can calculate that because that's the area under the curve between 0 and 0. Now think about that logically. If I'm at 0 and I end at 0, how much have I gone? Right, there is no area. I haven't gone anywhere. You have to have a difference in these in order for you to be able to calculate an area. If I'm starting at 0 and stopping at 0, I haven't gone anywhere to get any area. So this one is a 0. By the way, this is one of the like the laws for integrals. If these are the same values, the top and bottom limits, then your answer is going to be 0, which makes sense because you haven't gone anywhere to get any area. So the next one, the next integral for when x is 1 would look like this. Right? Because now my upper bound is a 1. My lower bound is always going to be 0 because that's what it started out at. So if I have an upper bound of 1, then let's see how far area. Area from 0 to 1 is, I guess I can highlight it out here. How much is that? So look at the box. Each box is worth 1. And I can pretty much count my boxes. Here's 1 box. Here's 2 boxes. This is a half a box. So this one will be 2.5. The next integral would be going from 0 to 2, right? Now my x value is 2 of f of t dt. All right, well now I'm going a little further, and by the way, these are all above the x-axis, so they're positive. Now how many boxes do I have? Well, I count them up. 1, 2, 3, and a half, and another half, make it 4. Next one, my x is 3. All right, now I'm adding on, I'm adding on this piece. So I'm adding on one more box. Now I was at 4, I'm adding one more box on, now I'm at 5. All right, next one. Now I'm making my integral go from 0 to 4. And now I'm adding another half a box on, right? So now I'm at 5.5. And then my last little one, 5.5 for this guy, and then my last one goes 0 to 5, and that is for f of t dt. But this time I have to subtract away a half. Right now my area is below the x-axis. And so if I take 5.5 and I subtract a half away, I get 5. And there you go. Complete the table. We did. All based off of that integral. It's called an accumulation function. You're accumulating area. So it's accumulation function. And so here's the fundamental theorem of calculus. There's two parts to the fundamental theorem of calculus. This is primarily part 2. Not that you care, but there's another part we'll talk about later. And here's what it says, and this is really significant, and I'm going to put it in words and bubble it and make it all bold and such in just a second. But if I take the derivative of an integral, guess what I get? I get the original function. That is crazy. If I take the derivative of the integral, they undo each other. They're inverses of each other. And so you end up with, if the derivative of the integral equals the original function. So that's what we want to put in words here. When you take the derivative of an integral, you get the original function. You get f of x, the original function. That is a huge concept for you to remember. Important, important, important. Derivatives and integrals are inverses of each other. They undo each other. They cancel each other out, just like multiplication and division. In example 1, the graph of f is the derivative of capital F of x. So capital F of x is considered the antiderivative. You went backwards. Antiderivative of f of x. So the capital F of x represents an antiderivative, different than a little f of x. There's a difference between the two things. There are some variations that come up. I don't know how much we'll see of these, but I'll show you real quick. This is equivalent to, remember you plug in your, well, it's f of b minus f of a type stuff, but here's what this one would look like. F of g of x times g prime of x. Because you have to put this bound in for your function, and then take the derivative of that bound. Now that happens, you want to use that, and we're going to see that when a is a constant. This is the rule we're going to use. If the bottom has a number as its representative, we're going to do this to it. But if these are both, let me do it in red here since I did the other ones in red. If these are both variables, then I have to apply this rule to it. Are you ready for this guy? It's kind of like a product rule. You're going to take f of g of x, multiply it by f prime of x, and then you're going to take f of h, subtract it with f of h of x times h prime of x. I think I want to fix that. I'm looking at what I've got written here. It's this should be a g, and I don't know whether it was from me copying from the video or not, but all right, that should be a g. Okay. All right, we're going to keep that handy for when we do some example problems in just a moment. Here it goes. Flip the page. Number 1. These are still examples. We haven't gotten to the practice stuff yet. So they want to know, find the derivative of this. Well, all you need to do, if this is a constant, is, and again, I'm going back to, I'm looking at this. I'm going to take f of g of x. In other words, f of the x value. We have x up here. And then I'm going to multiply it by the derivative of x. So I'm applying that rule, which means that f prime of x is going to equal, plug an x in, right? Plug an x in. That gives me 3x squared plus 4x. And then multiply it by, I'm going to take this whole thing, the derivative of this. Well, the derivative of x is just 1. So really my answer, I didn't really need to do that, but I'm just going to show you that that really was. There was a 1 there, not that we needed it, and that's my answer. Second one, pi over 2 is a constant. I have a constant on the bottom and an x on the top. And so I'm going to apply the same thing. So my f prime of x this time is the sine of whatever that top bound is, x cubed, times the derivative of that upper bound. The derivative of x cubed is 3x squared. You could put it with the 3x squared in the front. It doesn't really matter. That's really your thing. That's your deal. This one, they don't even give me a function. It's just an h of t. So you put an x, the 4x in for the t. I want to circle that and say, plug it in right there. Here it is, plug it in right there. So my capital F of x this time is going to be h of 4x times the derivative of what that bound is. So times 4. That's when you have a constant in the front. That whatever that upper bound is, you just plug it in for the variable in the function that you got, okay? And then times it by the derivative of that bound. Now these are different. You see how these are different? Now you've got 2 variables. And so now we're going to be applying this crazy hot mess right here. So I'm going to take the top bound, plug it in, times the derivative of that bound. I'm going to subtract away the bottom bound plugged in, times the derivative of that bound. Okay, so I'm applying that rule. That's what I'm going to do. This one's going to be a little bigger. So this one is f prime of x. Start with the top. So I have 5x. Remember, this goes in. So is this guy going to go in just a second. I have 5x now instead of 5t times the derivative of the top, which is a 1, minus. Take the bottom guy, negative x, plug that in. That's going to be negative 5x times its derivative, negative 1. So let's see if we clean this up. I have 5x on the first part. I have a negative 5x, right? So it turns positive, but then it turns back to negative, and that gives me 0. So I've got nothing, a whole lot of nothing. And the last one, number 5, this time my capital F of x. Again, I have variables in the top and the bottom, so I'm going to do the top first. The top is going to be, now I got to put this 3x in for the t. So watch this guy, he's going to be a little crazy. He's a 3x squared minus a 3x times the derivative of 3x, which is 3. And then I'm going to do the same thing with the 2x. They're going to look very similar. I have a 2x squared minus 2x times 2. Now they actually do want us to take it a little further, make it pretty. So let's see our algebra skills here. We have 3, this 3 in the back end, times, this would be 3x times 3x, 9x squared minus 3x. Bring this 2 over in the front here, times 2x times 2x is 4x squared minus 2x. And then distribute out your 2's and 3's and see if we can combine anything together. 27x squared minus 9x minus 16x squared plus 4x at the end. Watch your signs. Minus, oh, this isn't 16, is it? Try 8. 8's a better fit. There we go. So 27 minus 8 gives me 19. 19x squared. And 9 plus 4, negative 9 plus 4 gives me a negative 5x. And that's the story. There you go. Fundamental theorem of calculus. So we are going to pick a few from the practice problems and call it a day on this one. I'm going to pick, first of all, number 7. Ooh, know why I picked 7? Because it's got a trig function and you love them. All right, let's see what it would look like. My function's going to be my f prime of x. I'm taking, see, pi is on the bottom, pi is a constant. Sine of x is my variable. So I'm going to take that and put it in for the t spot. So it's going to be 1 over the sine of x. Sine of x goes in for the t. But then I need to multiply that by the derivative of the sine of x, which is the cosine of x. So you end up with a fraction that's the cosine of x over the sine of x. We can also call that cotangent of x. Or, put a little or in there. All right, there aren't really any others that scare me that much on this side. Let me maybe do number 12. We'll look at 12. I'm taking what's on top because 3 is a constant and plugging it in for the t. That's going to be this. Secant of g of x. Isn't that weird? But then I have to multiply that by the derivative of what that bound is, so times g prime of x. That's the best I got for that guy. He can't do any more. How about one with the variable in both ends? So if you flippy do the page, maybe we might want to look at, oh my, let's try 15. 15 is probably the messiest of them, so I'll give you the messiest guy. Some of them are relatively easy. All right, so this one, they have variables. Upper end, bottom end are both variables. And so I'm going to take the upper guy, x, and plug it in for the t. That's going to give me a 3x minus 1 times the derivative of x, which is 1. Minus. Now I've got to take a negative x squared. This is going to get a little more dicey. 3 times a negative x squared minus 1 times the derivative of a negative x squared is a negative 2x. So let's see if we can clean this up just a bit. I have 3x minus 1 times 1, so that's just a 3x minus 1. That's happy. But then I have a negative 3x times a negative x squared. Now notice where that square is. The square is part of the x term. It's not squared on the outside, which would turn that positive. So this is a negative x that is, you're multiplying by the negative 3, distributing that negative, makes this plus a 3x squared. Actually, I should keep it probably in parentheses for a minute. A negative negative 1 makes this plus 1. And the reason why I kept that in parentheses is because now I need to multiply it by a negative 2x. So, just that back part. I have 3x minus 1 in the front. I have a negative 2x times a 3x squared gives me a negative 6x cubed. And a negative 2x times 1 gives me a negative 2x. So final best answer, I'm going to go into this next box, is I've got nobody else cubing. I have no squares. The squares went away. So I have a 3x minus 2x, so I've got a plus x, and I have a minus 1, and that's my 15. All right. I'm looking to see, let's do 18. 18 will be the last guy, our test prep here. So 18 it is, multiple choice. Let g of x equal the derivative of the integral from 0 to x of the square root of t squared plus 9 dt. What is g of negative 4? Well, question number 1 is what is g of x? And g of x is the same thing. Forget about this derivative right now. G of x is when you take this x and plug it into your function, right? So if you take x and put it in here, it's going to be what your original function was. That's what the derivative and the integral are doing each other. So it would be x squared plus 9. And so then the question is, this was really more of a notation thing. If I put a negative 4 in here, I want to know what g of negative 4 is. All right, so take a negative 4, plug it in. Negative 4 squared plus 9 gives me the square root of 25, and I can see that that would be 5. This was kind of, they wanted to make sure that you understood what the notation was really talking about. If you take the derivative, which is what we were doing with all of these, f prime of x, you end up just taking that top guy, because this is a constant, taking the top bound and putting it in for the t, and then you can evaluate it out. All right, that takes care of section 6.4. Remember, you are skipping number 20 on the practice problems. So the next page, this one is 19, and then you don't have to do number 20. All right, have a great day, and I will see you in class.